All right, welcome to our explainer. Today we're taking Newton's laws out for a spin, applying them to two of the most critical concepts you'll ever run into in mechanics: friction and, you guessed it, circular motion. Okay, let's jump right in.
But first, let's start with a question to get your brain warmed up. What is that invisible force that literally lets you walk across the room and also keeps a car from flying off a curved road? It's a force that's all about opposition, and without it, our world would be a ridiculously slippery place.
The answer, of course, is friction. It's the star of the show for the first half of this deep dive, and honestly, you have to understand it to solve pretty much any real-world physics problem.
So, what is it really? At its core, friction is just the resistance a surface feels when it tries to move over another one. Sounds simple, right? Well, yeah, but the details are where all the fun is.
See, friction comes into two main flavors. First up is static friction. This is the force you have to overcome just to get something moving. It has a maximum value, and once you push harder than that, the object finally breaks free and starts to slide. And the moment it's moving, kinetic friction takes over. This is a constant force that keeps fighting the motion as long as it's sliding.
Now, the key to calculating friction is this thing called the coefficient, written with the Greek letter mu. This number is all about the two surfaces touching. Like rubber on asphalt is way different than ice on ice. It has no units, and here's the really crucial part. The static coefficient is almost always bigger than the kinetic one, and that's why it's always harder to get a heavy box moving than it is to keep it sliding.
So, you probably noticed in both of those friction equations that little term F sub n, the normal force. This is the force a surface exerts back on an object, and I'm telling you, figuring this out correctly is the secret to unlocking pretty much any friction problem. And here's the spoiler alert. It is not always equal to the object's weight.
Okay, let's start with the easy case. An object is just sitting there on a flat surface. Gravity's pulling it down, and the surface pushes right back up with a force that's exactly equal and opposite. So in this simple case, the normal force, Fn, just equals mg. Easy peasy. But what happens when we start adding other forces into the mix? Let's say you're pulling a suitcase. You're not just pulling it forward. You're also pulling it up a little bit. So how does that change the friction? Does it get stronger or weaker? And this right here is such a key insight. Because part of your force is pulling up, you're actually helping to lift the suitcase. That means the floor doesn't have to push up as hard. The normal force gets smaller, and since friction depends on the normal force, the friction gets weaker too. This is exactly why it's almost always easier to pull something heavy than it is to push it. The exact same logic is in play on inclined planes. On a slope, gravity isn't pulling straight down into the surface anymore, it gets split. Part of gravity's force pulls the object down the slope, and the other part pulls it into the slope. So the normal force only needs to cancel out the part that's pushing into the slope, which means it's less than the object's full weight. Okay, now that we've got a good handle on the normal force, we can start to look at some more complex and kind of counterintuitive setups, where friction is the hero. Think about this, holding an eraser against a wall. Just by pushing horizontally on it. What's stopping it from falling? Well, your horizontal push becomes the normal force. The wall pushes back, and that normal force creates static friction that points straight up, fighting against gravity. As long as that upward friction is strong enough to equal the eraser's weight, it's not going anywhere. We can take that same logic and apply it to connected systems, like a classic pulley problem from your textbook. For that block on the table to even start moving, the force pulling it, which is just the weight of the hanging mass, has got to be strong enough to overcome the maximum static friction on the table. It's a tug-of-war, and motion only starts when the hanging weight wins. All right, let's totally switch gears. We're moving away from forces that stop motion, and we're going to talk about the forces that create a very specific kind of motion, moving in a circle.
Here's the most important thing you need to remember. Objects don't naturally move in circles. Newton's first law says they want to go in a straight line forever. So to force an object to turn, you need a constant net force that's always pulling it toward the center of the circle. That inward force creates what we call centripetal acceleration.
And please don't fall into this common trap. Centripetal force is not a new fundamental force of nature. It's not magic. Think of it as a job title. It's the role that one of our regular, everyday forces has to play to make something turn. It's simply the net inward force. That's it. So, which forces can get this job? Well, lots of them. When a car takes a corner, the static friction between the tires and the road is playing the role of centripetal force. When you swing a ball on a string, it's the tension in the string. And for the moon going around the Earth, it's gravity. And now for the grand finale.
Let's pull everything together, friction, the normal force, and circular motion, to look at a truly brilliant piece of engineering, the banked turn.
Ever wonder why high-speed racetracks have those steeply tilted corners? It's because on a flat turn, friction has to do all the heavy lifting to turn the car. But if you bank the road, you tilt the normal force. And now, just like on that inclined plane, the normal force gets split into components. And one of those components points horizontally straight toward the center of the turn. It's helping friction do its job, letting the car take that turn way, way faster.
Which brings us to a final, really cool thought. If the normal force can help, could it do the job all by itself? The answer is yes. There's a perfect magic speed for any banked curve where the inward component of the normal force provides exactly the centripetal force you need. At that one specific speed, you could make the turn even if the road were a sheet of pure frictionless ice. Mastering these laws isn't just about passing a test. It's about seeing the elegant hidden physics that designs the world all around us.